Now let us look at the global part of the code. That is, if you look into the actual source code, we are looking at this part, that is outside main, this globally declared variables. Globally declared variables and data structures is something that we are looking into now, and we will see how and we will see where this data is actually stored by the compiler when it encounters these variables. So we feed this particular file into the compiler, and we saw the different sections mentioned previously, that is in the section header that we saw. Now let us see where all this data goes. We anyway talked about it briefly, that is the text section and the data section. Now let's look at it in more detail. So if you have a data which is, say you are declaring an array of characters, 8-bit values, and say you have 10,000 elements in that, and then you are declaring another array. Probably this is an array of maybe some other data structures. Now again, you have one data which is initialized, but it is not a constant data. Then you have some constant data initialized here, and then you have some data that is uninitialized. Okay, so we have different types of data that we have. Just to validate what happens, we have actually declared this data outside the main, so that we get a full understanding of which data goes where. So this is an uninitialized data. So all the uninitialized data, that is you have UI into 32T, that is it's a word length data, that is these two variables, test3 and test4 and test5, which is initialized to 0, and these uninitialized data, all of them go into the .bss section. So we saw the .bss section in the header information in the previous slide and in the terminal. Now if you have data that is initialized, it goes into the .data section. So, and this moving the information from actually populating the RAM during boot up with the .data values is a bit tricky, and the user has to write some code actually to move the data from the flash to the RAM, and we'll see all that. And then anything that is constant goes into the RO text section, that is this goes into the flash and it stays in the flash. It is not moved around because it's a constant. These values are not going to change, so these values are not moved around. So this is more or less what happens to the different types of data that the compiler sees. Now this is again an interesting slide. Now we will see it in the terminal as well. So this is the main program that we saw in the IDE, and we are actually, what we are seeing here is the disassembly of the particular code. So this, after you compile this is the dot text section, as you can see here, and this has a lot of information in it. For example, so this is the dot. So when you pass code into the compiler, when the compiler compiles the code, as we said, it creates a dot text section where it actually holds the code. Now we have asked for a disassembly view here for the code, and that is the reason we are seeing the disassembly view here. That is, we have the actual instruction and the breakdown of that instruction into assembly and machine language as well. Okay, so this is the assembly. This is the so see, say you say test3 equal to 4, which is a variable. So test3 equal to 4, and this variable was of course declared outside the main as a global. So when you say test3 equal to 4, these are the actions that the compiler actually takes in assembly, and then that assembly instruction again is converted into machine instruction. So what goes into the binary files is these string of bits. Okay, so see, there are 16-bit values. So the address location is, say, it starts from 0, 0, 2, 4, 6, 8, and so on. So this is the address. So address location. Okay, so that's a, the program counter starts from 0, then it will be 2, it will be 4, 6, 8, so on and so forth, because all these instructions are 16-bit instructions or 2-byte instructions. Now, whenever you call a function, or whenever you create a function, it the compiler actually prepares the stack. So this is not in your control. The compiler will be saving stack pointers, and it will actually be preparing the stack, because see, when it does sp subtracts sp 8 from sp, it is actually creating a stack space for this particular function, and it's making a lot of calculations here. Okay, so this is something that the compiler does. This is, you have started coding from here, but this is something that the compiler actually prepares the stack for the local variables here. Okay, that's what it does here. And then whatever you have, for example, you have test3 equal to 4, so you again fill, this is the assembly code for, so see, there is a lot of assembly being written for just a small statement that we write in C. Okay, so this is where the value is actually filled in. Okay, so it's actually filled into a register. So assembly will not understand variables, so it is a job of the compiler to convert this into assembly. And as far as C language is concerned, we will think that we are using variables, but when it comes down to assembly, there is no such thing. So, but we get the results we desire here. Then a test5 plus plus, so we increment some value, and this is the assembly code for that. So far so good. Okay, because the test3 value is here. The compiler knows that the test3 is from the same file. It assigns a value of 4 and all that. Stuff becomes a little bit weird when it comes to this section of the code. It calls a function called PLL init. That is the initializing of the PLL. But when a compiler looks at a file and it starts compiling it, and the file calls a particular function, it looks at the function declaration in the header, whether the function is declared or not. But it does not at that point check where the function is residing. Okay, it does not check where the function is residing. It just does this. That is, it just does a BL. So BL is branch and link. So this is nothing but loading the program counter with the value where the function resides, but it is a 0 here. Can you see that? It's a 0 here, and it's an ARM thumb call to PLL init. And all of this information is put in here because this is not yet resolved. This is not yet resolved. So that's why the branch addresses will be fixed up by the linker during linking stage. So that is the job of the linker now. The compiler doesn't know where the function is. We know that it is in the core initialization file, but when we feed all the object files into the linker will search for this particular symbol, and then it is going to fill up this address depending on where it is. Now it is easier said than done. All of these addresses are going to be adjusted as well, and which we will see going forward. For example, this is again enable sysdig. There's a function called enable sysdig, and the compiler does not know where it is, so it just keeps it at that. And there's no harm in it, because the linker is going to come in now, and it is going to make the corrections here. It is going to put in the right addresses, and when you get the final code, if you have not made any mistakes in the linker, you should be able to see that it has been populated with the right addresses. So basically, the compiler and the linker makes our life easy. So there's nothing to be afraid of these tools. There is a lot to be afraid of if you had to hand code the entire application using machine language. As you can see, it is very difficult to do it this way, which the compiler and the linker does for you. So the compiler, linker, the toolchain is your friend. It is not there to scare you. It is there to help you. Now, moving on. Absolute addresses. That is, when we say absolute addresses, we will see that, for example, we are looking at, so here we are actually configuring some registers actually of the controller. When we are configuring some registers, they will have some absolute address. That is, in the RCC PLL configure field is going to be a fixed address. Okay, so that is stored in the flash. So absolute addresses are stored in memory locations as words. Okay, here these memory locations are addressed related to the program counter. The linker has to fix this addresses at link time. So it's 7A, 7C, 7E, 8082, 84, so on and so forth. Now this will be in the flash, but these addresses will again be changing, which we'll see later. So these addresses will change. The linker will have to fix these addresses up. Okay, but otherwise these absolute addresses will be 4 bytes, which will be residing somewhere in the flash, and addressing these, that is addressing this, getting this address will be using an offset to the PC. So it is going to be 152 bytes. So this is in decimal, so 152 bytes from here, and then this is 148 bytes from here. So because it is moved closer to this location, this is 148 bytes from here. So this is what, so we say we are talking about this value. So both these are actually addressing the same value, and it is this. Okay, so and this is in the flash, and these addresses are going to change, which we shall see shortly. Now, to view the text section in the object files, you need to run the objdump command. So you need to do so this is the objdump command. So if you run this command, you will be able to see the .text section that we saw. It will give you full information about the object file, but we will focus on the .text section for now. This is the same stuff that we saw previously in the slides. So we talked about this part, and this is the main program. So this is the command that we executed, arm eabi objdump and arm none eabi objdump, and this is the command we executed, and this is what we got. We, of course, the sections information comes first, then we have this. We'll talk about the symbol table later. So symbol table is something that is extremely important for the linker file, and we'll talk about it in detail later. So let's focus on the text section now. This is what we saw, and we talked about PL0, that is when it cannot find the address. Another thing it does is, suppose it's a local variable within the function. So any local variable within the function will be handled within the function on the stack itself. Right? So this is not going to be visible in the symbol table. We'll see that. If the variable was a static variable here, suppose you declare a static variable within a function, that is a variable that you'll probably see in the symbol table. And then this is the function, and this is the while loop that we saw. So this is the while loop. So when you have a while loop here, that this is the assembly corresponding to the while loop. See that? So when you have a while one, this is the assembly code corresponding to that. Okay. So BN3C, that's all. So it's like goes back to 3C and it keeps looping. Okay, and there's a NOP, no op here, and then there are two variables called test3 and test5, which is put here. Okay, so let's see what is test3 and test5 in the main code. So you have test5 which is equal to 0, and test3 is an uninitialized value. So it is representing those values here. Now these are again the test3 and test5. Of course, they are globals, and like we saw in the like we saw in the slide, these variables will be going into different sections of the, so test 3, test 5, they'll all go into the BSS section again. Now similarly, we can have a look at the other files, that is whatever we had compiled. So we now let us look into the core initialization object file. The core initialization object file is a bigger one, so we'll have a lot of information. Disassembly information will be, there will be a lot of information in the text section. So you have a PLL init function, and all the assembly code for the PLL init will be here. Then you have the and one line of C code amounts to a lot of assembly here. So all that hard work the compiler is taking away from you, and it's doing that in the background. That's conversion into the binary format. So this is how the disassembly looks like. And then you have a delay function. The delay function will again have a disassembly, and so on and so forth. So all these functions, if you want to look at the text section looks like this in the object file. But when we are flashing this object file into the on the board, all this information goes away. We will have to do a obj copy, and all of this, whatever you have, these the information about symbol table and sections and so on and so forth, all of them go away, and what is copied is only this part, the instructions, the machine instructions. Nothing else stays, no other instruction stays. So it's dot text and dot data go in with only the binary. Rest of the information is not visible here. For example, here you see a disassembly will not be visible in the case of your binary that gets loaded onto the board. There is something interesting that we can also verify. Okay, let us look at the third file now. Let us look at the third file, and then we will, as a side note, we will see something interesting. So let us do startup gcc.o, and then startup gcc.o will again have its layout. Again, it has a section information symbol table, and then you have the reset ISR value. This is the text section, so you'll not see that there's a big vector table which is not visible here, we are only seeing text section here. So the vector section is not visible here. Okay, that ISR vector. So again, that only has the functions listed here. Of course, there's a reset ISR, which is a function that happens during reset, and then you have nm ISR. Okay, you have fault ISR, and so on and so forth. So all the handlers, you can see the code for all the handlers in the startup file, but the startup file has got a lot of other components involved. Okay. And we will have a look at we'll have a detailed look at how the startup file is organized, and how to populate the startup file. Very important. And once we are completely comfortable with this chapter on linker and makefile, shall we look into the startup file, and we'll see how it ties into the concept of linking as well. So anyway, now as I was saying, let us check up something interesting. So we'll do a compile here of but we'll do a compile without the debug option, and we'll see what happens to the output. So we are doing a compile here for the build example main.c, which we did previously, but we'll not have the debug information here. So So of course the output file is going to be smaller. That's one effect or one outcome of not having the debug information involved, but something else will happen. So let's run the obj dump command again on the build example main. Okay, so let's see. So we are running the same obj dump command on the build example main, and we'll check up how the output looks like now. So we can see the sections, but the sections are much smaller now because the debug sections are gone. Can you see that? Only text, data, BSS, RO data, comment, that's it. There is no debug section. Here in the previous dump, if you see for the other files, you have this, and we saw this for this main program also, but now debug section is when you look at the code, you don't see the source. That is, you don't see the C statements anymore. And that happens because the -G option is missing. Because the debug symbols have to be there to tie these assembly instructions with the particular source code. If the debugging instructions are not there, then you will not be able to see the source. Here, you will only see the assembly. So even if you give the option of -S in obj dump to see the source code, because there is no debugger information, you'll not be able to see the source. So I thought that it's an interesting side note to share with you. So whenever you want to see a mixed view of source and assembly, you need to compile the code with -G option. Otherwise, this will not work.